Hi guys, I'll introduce you in Russia and then we'll switch back to English, please.
All right.
Sebastian Theophil изучал компьютерную сайенс в Берлинском и Тулузском институтах. У него есть PhD по Computer Science из Humboldt University of Berlin. Также он работает в ThinkCell с самого основания компании. И его в качестве эксперта выступает Михаил Матросов, который постоянно является участником C++ конференций по всему миру, и C++ Russia в том числе. Выпускник ВМК МГУ, был сотрудником там же в лаборатории компьютерной графики и мультимедиа, и был разработчиком-экспертом в R&D офисе Align Technologies. Я крайне настоятельно рекомендую посмотреть его прошлогодний ток по спецификаторам, квалификаторам и шаблонам. Мне очень зашел. So, guys, welcome. Let's start your interesting talk about cross-platform programming and details on that.
Thank you. Thank you very much for the introduction. Okay. So hi everyone. I'm Sebastian, and today I will talk about the lessons we have learned from cross-platform development at ThinkCell while we try to port our software from Windows to macOS and later in some small parts to the web as well. So what was the problem we were starting from? We had been doing about 12 years of development on Windows only. And in that time, we had written about 1 million lines of C++ code. And you can imagine that in that time, we had used the Windows API everywhere throughout our code base. And we had used Windows data types, hresults, handles, etc. through the code base as well. It's important to know that our product is an add-in, which is dynamically loaded in Microsoft Excel and PowerPoint. And that has some important implications. It means, first and foremost, that we're not in control of the main application, actually. And unlike people who do embedded or server development, we are not in control of the computer itself either, of course. That means that we have to be very flexible in some regards. For example, we have to be able to render into any object that the main application would give us. This could be NS views on macOS or core animation layers. This can be H windows on Windows or DirectX textures. We always wanted to have a renderer with a DirectX backend on Windows because that's what was best supported and that was what Office used, and an OpenGL backend on macOS. So we had to be flexible there too. We don't share the main message, the main event loop that belongs to the main application. And we always wanted to support the platform-specific features our host application supported at the same time. That could mean very little things like PowerPoint on macOS supports the triple click, which selects an entire paragraph of text. So we wanted to support that too, to minimize the friction between our add-in and using PowerPoint. And it could mean bigger things like Office on the Mac is running sandboxed, and that automatically meant that we were running in a sandboxed environment as well. When we started porting ThinkCell to macOS, we were looking for a cross-platform toolkit that would just hide all the platform specifics from us and would simply behave identically on all operating systems. I mean, that's the holy grail. And my talk is essentially about why this does not exist, and why it's actually very hard to get such a toolkit. In my talk, I will go over a couple of problems that came up or the solutions we found to them. And I hope I've arranged them in a meaningful way so everyone can draw some lesson from this talk. And the first problem I will talk about is how to find the right level of abstraction for a good cross-platform interface. Let's look at a small motivating example. How many ways are there to rename a file on the only 2 operating systems that we really support? Turns out there are quite a lot. There is the movefilex API on Windows. There is the POSIX rename call. There is the Darwin macOS extension rename X and P, and the copyfile API, which also can rename files. Then there are cross-platform toolkits. Qfile has a rename function. Boost File System has a rename function. And then there is the odd man out in the macOS AppKit framework There's the Objective-C function, NS file manager, replace item at URL, etc. So who would know off the top of their heads which of these functions replaces the target file if it already exists? Or which of these functions will return an error when the target file already exists? Or at least lets you specify you want an error returned? Which of these will really move the file when source and target file location are on the same disk volume? And which of these can do so atomically? And to make matters a bit more complicated, which of these functions would copy the access control list from your source location to the target location? Or which ones would adopt the default ACL at the target location? Now, all these are very meaningful, very important question for the two operating systems that we are working for, or just for the performance of your system. But they're pretty hard to answer, and these functions all give kind of different answers to these questions. That shows it's very hard to get identical semantics when you're working on different operating systems. The good news for us is, in that case, I would argue we don't actually need a cross-platform file rename function. This is the wrong level of abstraction. We need something else entirely. We need functions to maybe create a user application settings file, or create a temporary file that will be automatically deleted when the last handle to that file is closed, but which can be opened by other applications in the meantime. Or we need a function to download a file to a cache in a thread-safe way, so no other thread or process will ever see a partially written cache file. Or we might need a function to create a document in a user-specified folder, which would imply opening the system-specific save file dialog, and maybe on macOS create a sandbox exception for that location. So we need functions with very strong and identical semantics. And when we define our functions from the perspective of our application, when we define what we actually need in very strong terms, then it often becomes much easier to implement them on each operating system. And sometimes you can do that in very different ways. So let's look at the simplest example. How many choices are there to make when you just want to create a user application settings file? So on Windows, you would want to save that file in the app data folder probably. We might want to create a ThingCell subfolder there, of course. App data instead of local app data already implies that this settings file will be roamed when the user profile is on a server, which is a good decision because the application settings would be the same regardless of where the user logs in his account. But then on Windows, processes can run under different integrity levels. And if you run a process once with a high integrity level, and it will save the settings file, and then you run it again with a lower integrity level, it would not be able to read the settings file it had just written. So we can say, for example, we want to encode the integrity level in this ThingCell folder name as well. Now, these are decisions that are most or only relevant on Windows. On macOS, we have to make very different decisions. We first have to decide where to store the file. If we are not sandboxed, we could just store it in library applications toward ThingCell. If we are sandboxed and we want the file to be shared between different applications that we have written, we could store it in a group container for our application group. And then there are more decisions we would make now that we know what the function is actually there for. We would say, okay, we probably want to lock the files while we write and read them. We want to inherit access control lists from the parent folder when that is meaningful on our operating system, because the parent folder is a system folder and presumably has the right access control list set. A slightly more complicated example is how do we create temporary files that will be automatically deleted when the last handle to them is closed. On Windows, this is pretty straightforward. We create a temp file in the system temp folder. Then we give it suitable security attributes. We want to prevent file execution probably. We make it accessible by the current user only. And then there is a magic flag on Windows, file flag delete on close, which exactly does what we want. It says when the last handle to that file is closed, Windows will delete this file. So that's very handy. We then just have to synchronize access to that file. Now on macOS, we can implement a function with the same semantics because The semantics are useful to us, but it's a bit more work. We will create the file in the application group container folder because we want it to be shared with other of our applications. Again, we will prevent file execution maybe, we synchronize file access, and then we have to solve a couple of macOS specific problems. The open call can be interrupted on macOS or all POSIX systems by a signal, so we have to handle interrupt. And then we might have to implement manual reference counting of the temp files we've just created. macOS does not guarantee they are deleted automatically. We want to delete them as soon as possible. Maybe manual reference counting in shared memory is a good idea to do that. We could implement a simpler solution as well. We could say, okay, we delete this file only if our application is restarted, and then we delete all stale files. This is now a degree of freedom that we have. So I say it's very important to have well-defined and strong semantics in your cross-platform interface. That makes it much easier to implement these functions correctly on each operating system. If you have functions with too weak semantics, then you get subtle errors because you don't really know what is this function really doing on my operating system. So it's a big warning sign if you start to look into the implementation of a function, let's say of boost file system rename, to find out what it really does on Windows. And you have to find the right level of abstraction. So there's one mistake you can do is you introduce a cross-platform interface at a too high level of abstraction. Then you would miss a chance to unify a lot of code that would actually have been the same on each operating system. In my experience, this is not a mistake I have made very often. I've usually made the opposite mistake. I try to introduce cross-platform interfaces at a very low level of abstraction, like almost right above the operating system. And so this chapter was about why that's usually, or very often, not such a good idea. Because very often you end up forcing identical interfaces on very different things. So for example, the result might be that the semantics you now introduce don't match one of the operating systems very well. So this is what qfile set permissions does, which forces the POSIX permission model on Windows, which you can do. You can implement that on Windows because the Windows security model is very powerful, but that's not really what Windows does. Or the other mistake is that you just lose a lot of the expressiveness of the underlying operating system because you start to write the least common denominator of all the operating systems you support. And this is what boost file system rename does, and this is in a way also what POSIX rename does. It's the most bare bones simplest function that is hardly usable or useful at all. Now I would go to the next chapter, unless there are already questions now. Is there any question?
No, there are no questions side. Nope.
Okay, then I'll just keep going. Another problem that can happen is that while you're interacting with the operating systems, you get objects with similar semantics, but with very different lifetimes. And this can cause a lot of problems as well. We use shared memory a lot in our application to implement inter-process communication. Now, I've said initially that our tool is an add-in in Microsoft PowerPoint and Microsoft Excel, but that's really only half the story. There are a lot of other processes involved. So we have a Google Chrome extension that lets you import data from the Tableau.com data tool. We have a command line tool that lets you batch create presentations from a template and data you have in JSON file format. There's a chart scanner that lets you extract data from charts that you might only have as an image in a PDF report maybe or on a website. And it uses image recognition and character recognition algorithms to read the data labels, to read the axis values, and estimate the underlying data values. And then last but not least, we have processes that just do OAuth authentication, so we can download images from Getty Images, for example, for the user. And all these processes have to communicate with each other and send data back and forth. We use Boost Interprocess for that because it does offer a common API for shared memory on Windows and POSIX systems. And it supports like the essential building blocks that you need. So it has named memory objects, of course, that you can look up in each process and then map into your process memory. That's interprocess managed shared memory, for example. It has a smart pointer or a pointer type offset pointer that you can store in shared memory. This is relatively interesting. So you want to put a std vector, for example, in your shared memory. The std vector internally holds 3 pointers. But it cannot now, as a std vector in shared memory, it cannot store actual pointers because the memory address in each of the processes will be different. You map the shared memory at different locations. So instead, offset pointer does a clever trick. It stores an offset to its own this pointer. And these offsets would be the same in each process. And then last, you need synchronization objects, of course. So how does that look in code? For example, like this, I write a very simple server process, and that server process creates a managed shared memory object with a given name and a given size in bytes. Now this name has to be pretty specific. You might want to make it specific to the build version of your tool, to your current host, to the security identifier your process is running under, because sometimes these names can live in a global namespace, and you want it to be very, very specific. And when I've created this managed shared memory object, I can construct an object, here a std pair of double and int, in that shared memory and initialize it. And in the child process, I do the same. I create a managed shared memory object with the same name, and I can look up this object. So this is pretty cool. It's pretty magic when it works. Now let's say I have this bit of code, and I run these processes, I terminate them again, I start the server process again. So what happens? Well, what happens is that this line will throw an error, and it will say, this shared memory object already exists. And if, like me, you've done most of your development on Windows, this is pretty surprising. Because, I mean, it's memory after all. And I've deleted all my processes and now restart them, and the memory object still exists. And as a Windows programmer, this also means that Boost managed shared memory does not use Windows shared memory, actually. That would look like this. On Windows, you can create a shared memory object by creating an anonymous file mapping. So you create a file mapping and you pass it an invalid handle value, which to Windows means this file mapping will be backed by the page file. And again, as we've seen with temp files, Windows will tell you, okay, when the last handle to that file mapping is closed, I will throw away the backing memory for you. And this is a great feature. This is a great operating system guarantee. This is a feature you want in, I guess, a lot of circumstances. But this is not a feature that is supported on POSIX. And this has by Boost Interprocess, for example. And this has created a lot of problems over the last few years. I mean, I did a bit of Googling when I encountered this problem, and this has come up in oh so many ways over the last 11 years only with users of Boost Interprocess, and hasn't really been fixed at all. Like I said, on Windows shared memory objects, mutexes are reference counted. That means when the last handle to them is released because the process has terminated, for example, then that resource is freed. On POSIX, shared memory can be either file-backed, which means that the backing file will still exist even if the processes crash, even after a system reboot. Or you can use POSIX shared memory, which still means that the backing memory will persist until your computer is rebooted. And that kind of assumes that you implement a server-client model, like I've shown initially, where the server really owns the memory object and is responsible for deleting it when the server is restarted. If that's not your model, nor your process model, and it isn't our process model, then you are out of luck. I could find about 2 or 1.5 solutions to this problem, actually. And Boost Interprocess and Qt implement neither. So the first one was using robust mutexes. Robust mutexes are pthread mutexes with an additional attribute. So you can declare pthread mutexes as being process shared, which means that you can allocate them in shared memory. And then you can declare them as robust as well, which means that the pthread mutex will hold additional bookkeeping data. It will keep track of who last locked it. And when the pthread mutex does that and you try to lock it, it can tell you, oh, the last process that locked me has died while holding the lock. And then it returns eowner dead. And that's pretty useful. That can tell you, okay, my whatever resource I'm guarding really here is probably in an invalid state. And I have to reinitialize it. Here I have to reinitialize my shared memory. It is maybe only half a solution because you still have to solve the problem that the last process terminated unexpectedly and it did not hold the lock to your shared mutex. There is a boost interprocess pull request that might need some support. It's lying around there. It's not by me, but it's a useful addition to boost interprocess that hasn't been going anywhere really, and you might want to look at that. The solution that I found, because macOS doesn't support robust mutexes anyway, is using file locks. That was the only other resource I could find that had actually process lifetime on POSIX systems. And there's also a huge warning here on the slide because file locks on POSIX systems are very weird as well. There's a boost interprocess pull request by us. I'll show you what it does on the next slide. You might also want to look into that or use it or comment on it. So what do? We introduce another shared memory object into boost interprocess, non-persistent shared memory, which complements the Windows shared memory object that boost interprocess implements on Windows. The two now have compatible semantics. And what we do internally is the following. So there's this very internal method that creates the backing file. We try to open or create this backing file, and we try to acquire an exclusive lock when we do so. When that succeeds, we assume that we are the first and only ones to have opened this file, and we truncate the file to 0 bytes. So we throw away the stale, invalid data. And when we have done that, we degrade our lock to a shared lock and go on with our life. If the initial call to open failed, there are a couple of error conditions that we have to check, but we can finally conclude at some point that opening this file only failed because we could not get the exclusive lock, so we were not the first ones. So we just wait and try to get a shared lock as well. That's pretty simple. It seems to work in practice for a few years now, but it does have actually two problems in the details that I still think are not problems, luckily. So the first one is that this flock call down here that wants to degrade the exclusive lock to a shared lock. This one isn't actually atomic. It looks like it should, but it isn't. It will first release the exclusive lock and then reacquire a shared lock. This still seems to work, in my opinion, because there are only two cases that can happen here. The first one is that there's another call waiting here, waiting to acquire a shared lock. And that might succeed before our flock call succeeds. That doesn't seem to matter. The order in which those shared locks are acquired does not matter. The more interesting case is that while flock has released our exclusive lock, somebody else might come along up here and acquire an exclusive lock as well, and would also think that he's the first one to open this file. That would mean that the second call to open would acquire an exclusive lock and would also truncate the file. But then the file is truncated to size 0 twice, and both go on with shared locks. Also seems to be okay, actually. And the other problem is that network file systems have problems with file locks. So the file locks we create here might not be visible on other machines that have the same volume mounted. This does not seem to be okay as long as all these logs we're taking here are visible locally. And that's what NFS seems to support well. You mount with local logs. And I think from Googling that macOS does not work well at all if you have not local logs enabled, at least on your NFS home share. So I think we're good. If anybody disagrees, I'm really eager to hear your opinions. Now here, aiming for strong and identical semantics in our cross-platform code meant we wanted strong guarantees. And that means strong operating system guarantees. These are almost always a good thing. And it's not worth sacrificing operating system guarantees just to gain an identical programming interface to something. That's what Boost Interprocess did here. They said, okay, implementing the Windows semantics on other operating system, that is hard. It might not always be possible, or it might only be possible if you make certain strong assumptions. So they went the other way and used the weaker POSIX API and implemented that on Windows and gave Windows users, in my opinion, strictly weaker implementation. So even when you have cross-platform toolkits, getting to those good, strong semantics may be hard and may be actually left to you as a programmer to do. So throughout the talk, I will keep track a bit of which operating system had the better semantics. And here that point clearly goes to Windows. And we transported the Windows semantics to macOS. Are there any questions at this point?
Yeah, there is a question. If the second process gets exclusive lock, the first one will fail to get the shared one. Is it correct?
I mean here. You mean what was the question again?
Yes.
Can you repeat that? So the first
process
process will get
gets
the exclusive lock, and the second process will fail to get an exclusive lock. Yes.
No. Right. So the question actually asks the opposite. If the second process gets an exclusive lock, I mean, we are currently in the first, so we degrade the lock, and the second gets an exclusive.
So while we are here, we degrade the lock. We have released the lock. A second process comes along, calls open, and acquires an exclusive lock. That can happen.
Right.
Yes, that can happen, and then the second process will also truncate the file again. But then we have deleted the file content twice. That the second call doesn't seem to matter to me. And then both will go on with a shared lock.
Thanks.
Is that an answer to the question?
Seems like yes.
Yeah? Okay. Another thing that can happen is that while you're interacting with operating systems, well, they just behave differently, of course. And one such case is when you're handling mouse events. So superficially, Windows and macOS have a quite similar event handling architecture. Here I have implemented a little mock window with the help of some ATL. And on Windows, you have to declare or you have to implement a message handler, and you can do that by declaring this this message map. I tell him here that I want to handle mouse move messages, button down messages, button double click messages, and tell this little macro which functions should be called when such a message arrives. That's very similar in spirit to what macOS does, where I can directly overload a function on an NSView here, and the underlying AppKit framework will actually receive the operating system messages, will process them, and find out which function to call. So still, that looks to do about the same thing. But the devil is in the details, and the semantical differences here are very large. So first, the coordinate systems would be different on Windows and macOS for mouse events. That's maybe not so interesting. Windows only supports single and double clicks, whereas macOS supports an arbitrarily high click count if you click with the mouse very fast. On some events on Windows, some messages on Windows are opt-in events that you have to register for. So the mouse leave event, for example, you have to register to receive that for each window. So you have to keep some state already to remember to do that. On macOS, again, that would be automatic. Windows does not distinguish between mouse move and mouse drag events. Again, that's state that you have to keep. And most interestingly, on Windows, you have to capture the mouse manually. to receive mouse messages even when the mouse has left your window. There's one typical use case. The typical use case is the user presses the mouse button in your window. For example, it wants to resize an element in PowerPoint. It clicks on the corner or presses the mouse button and starts dragging. And while the user is dragging, he leaves your mouse window, like I'm now leaving the window. But you still want to receive those drag messages until the mouse is released again. And so in order to do that, you have to call setCapture and release capture manually. Again, there's a state that you have to keep. That's automatic on macOS. And last but not least, the message order on Windows can be very surprising. You can receive button down, button up events in pretty much any order. You can look at the code, for example, for Qt, for the Q Windows mouse handler translate mouse event function, for all the state they are keeping to handle this problem. On macOS, the order of events is always pretty clear. You receive mouse moved events until a button is pressed, then you receive mouse dragged events, and then you receive the same mouse up message again. Here, it's clearly macOS that had the saner semantics with the stronger guarantees. The guarantees that we wanted in our cross-platform mouse UI handling code. So what we had to do here is to implement a state machine, to sanitize the Windows craziness. And that state machine, I'll just give you an overview, is at its core pretty simple, but it was a very powerful tool to clean up our code. So you want to replicate the macOS behavior. So you have an initial state where you just receive mouse move events. And you keep track of which window is receiving mouse messages. And then when that window changes, you have to call track mouse event to receive the matching mouse leave event. And then there's a state transition when you receive your first button down message. You keep track of which button was pressed. You call setCapture to receive the further messages until the button is released, even if that's outside your window. And now you're in a state where you will ignore all other button presses until you receive one of two messages. Either you receive the message that the button you are tracking is released, you ignore all other button up messages, or the entire operation is canceled because you receive a cancel mode message. That means some dialog popped up or something. Or capture changed, which means some other window stole mouse capture for you. And then you just cancel the whole mouse operation. So now we've kind of replicated the macOS behavior only on the Windows side. So here, aiming for strong and identical semantics meant implied having strong invariants that hold on each operating system, which made our code much simpler. It reduced the number of states that our cross-platform UI interaction code had to handle dramatically for Windows. So that point here clearly goes to macOS because it looks simple in hindsight, and Qt does a little bit of that. But it's something we only found out after we ported our software to macOS. We found out how simple life could be, really. Again, questions? Shall I answer a question here?
Could you please clarify? So with this state machine, you was able to replicate the same guarantees on Windows as on Mac, which are as strong as on Mac. Is it correct?
Mm-hmm. That is correct.
Oh, that's great. That's great. No other questions. Please go on.
Okay. Because I mean, there's the funky case. I don't know how many developers do that, but I have two mice, for example. I have one for my left hand, I have one for my right hand. And you could receive messages for both of these mice in any kind of order. That's not something you really have to handle in your code. I mean, if you're dragging, then the other mouse doesn't matter that much. Now my talk changes a bit and focus a bit, and I will talk about in the remaining chapters. I will talk a bit more about tools we have built for our cross-platform software. And the first tool we've built is also more C++ related actually than the previous parts. Concerns text translation. Now, text internationalization in general is more than just translation, but today I will focus on translation. And any translation toolkit has to have 3 important features. You have to annotate the translatable texts in your code base so you can extract it easily. This translation sometimes needs context, so the translators know what you are talking about. And last but not least, there are a couple of complications because languages are pretty different. And apparently, and I hope I got this right, I didn't check with my Russian colleagues actually. Some languages like Russian have, for example, different plural forms or a different number of plural forms than English or German. The general flow for text translation is always the same. So you have this text annotation, you have the annotation of translatable texts in your source code. You extract all these texts with GNU getText or whatever. Then you send that off to the translators. And you get it back in an XML format, the XLIF format, which stands for XML Localization Interchange File Format. And then you import that into your project. And at runtime, your translation tool will look up the original English string in that translation database and then display the one that, or return the one that's correct for your current UI language. Now here, supporting different operating systems mechanisms to do that, that would be insanity. You want the same markup throughout your entire code base. You want to have a single extraction run that will find all the translatable text and dump it for the translators. And at runtime in your C++ code, you also want a uniform access mechanism. You don't want to have translation calls that return sometimes reference counted NS string pointers and at other times heap allocated basic strings. It would be great to have a tool that just returns card pointers with no lifetime issues. Now Boost Local would do all of that for us. It has been introduced into Boost pretty recently, and it does all 3 of those things. We have a translate function that also serves as a text annotation. You can translate with a context. Here in the second example, I want to translate open into German in the context of opening a file, that is öffnen. And last but not least, it supports different plural forms. So here it hopefully chose the correct Russian plural for having 3 files in a directory. And then, as I've said, this translate function in the background would look up the English versions in its catalogs, make a runtime lookup. So that's handy. It's good to have that. But we have C++20 now. This is not 1995 where we have to do runtime lookups. We have const expr functions, and we can do this way cooler, actually. So this is what our solution looks like. So we have an enum here. We have a couple of supported language. I've reduced it here to English and Russian. And then let's say we have a translatable string, which is just an array of translations. And the translate function would return the correct one, depending on your UI language. So that's straightforward. And then this is the magic sauce. This trans lookup, here I've left it as a macro. Trans lookup, which takes the string to translate its translation context and returns the correct translatable string. And then you can just chain that together and translate cancel as in Windows dialogues to Russian, for example. So how does trans lookup look if it's not doing a runtime lookup? Well, it's calculating a compile time hash. We take the string to translate and the translation context and calculate the murmur hash at compile time. The murmur hash would return a 128-bit hash value. There's no 128-bit built-in type, so it actually returns a pair of 64-bit integers. And these 64-bit integer values are then compile time hash lookup keys. So here we have this translatable string map data structure, which takes these 4 64-int hash values. And our build tool, the build tool that takes the XLIF file that is returned by the translators and processes it, will return or will build CPP files of template specializations. So it will calculate the same murmur hash we are calculating here at compile time, but it will compile it, calculate it once when it processes the XLIF files. And this is the output. It will CPP files full of those template specializations. And so here it has hopefully chosen the correct translation. And our const_expr functions are very cool, and this was actually very simple to do. It has one downside. I should say that for the sake of honesty. There's one downside to that approach, and that is that we cannot ship additional languages. So if you have runtime language catalogs, you could imagine that they are sitting in some folder and you just ship an additional translation. We can't do that here. They're all built in. So reminder, what are const_expr functions? They're very powerful. They're of course implicitly the same as inline functions. Both are calculated by calculated by the compiler, of course, so they can be inlined. And they must accept and return only literal types. And literal types can be quite a lot. They can be all scalars, integers, doubles, etc., of course, and references. Aggregate types are literal types, so anything that you can write with brace initialization, for example, std arrays. It can be arbitrary structs that have a const_expr constructor and destructor, but all their data members and base classes have to be literal types as well. So, for example, std pair double and int has a const_expr constructor. And all arrays of literal types are literal types themselves. Const_expr functions cannot be virtual, of course. They cannot contain goto or try catch. That's not such a strong limitation. But what makes them powerful is that they can contain if statements, switch statements, all kinds of loop statements. They can contain local variable declarations, as long as these are always initialized and literal types themselves. And, well, last but not least, you can't have virtual base classes. Well, that's not important to our hash function. So our hash looks like this. I mean, I spare you the actual real implementation because that's just a pretty straight port from the code on the GitHub repository. So we have a std pair of 64-bit integers that is returned from the hash function. The hash function can be templated. Here it is templated on the size of the string array. Internally, you see it can access the pointer to the beginning of the string array, etc. So the actual implementation is then pretty straightforward. Here, going for strong and identical cross-platform semantics meant that you also want to have cross-platform build tools that run the same on each operating system. And again, that makes your life much easier, like being able to extract all the translatable strings on each platform. I give this point because I've started the scoring thing. I have to give a point now. I give this point to Apple, to macOS, because Xcode actually had support for all of that, as long as it only runs on macOS. Whereas the Windows support is pretty lacking. Are there any questions regarding this part?
Yeah, but I think we should save them up to the end.
Mm-hmm. Okay. Now the next pretty cool tool that we have built is our error reporting tool. And I think we have given talks already about our approach to error reporting. And we have a pretty powerful error reporting architecture. In our code, we use asserts very liberally to check invariants in our code. And what's very important and different to other people, we leave those asserts even in release builds. Additionally, we also check all error codes that are returned by system APIs. And we always distinguish between expected and unexpected errors. So for example, when you open a file and that file does not exist, that's always an expected situation. That's not an error. But the operating system might return all kinds of other error codes that you actually don't handle because you've never seen them before. These are unexpected, and we consider them an error. And once we encounter such an unexpected behavior, we, first of all, well, we might decide to show an error message to the user, of course. But what's more important is that we always create an error report that we send home to our backend servers. And our backend can analyze this error report. It can find out if we have already fixed the bug. It can find out if we want to have more information from the user, how to reproduce this error. And it sent that information back to the process that has encountered the error. And then we might show a more precise error message. Please send us more info. Please contact support, etc. Or it might just silently download and install the update that will fix the error you just had. So this is pretty cool. This makes our software much better, I think. On our developer side, we have a tool where we can query this error report database. We can check which errors occur only on macOS, only on Windows, in which builds do they occur. And of course, we can then enter the information. When is that bug fixed? What shall we ask the user when that bug happens, etc. And our backend pre-analyzes bug reports. For example, it bins them according to the location in the code where they happen. So we put all of them together in one bag when they happen at the same line of code. So we can find out where are the problems occurring. And it can also, the backend also walks the stack to show us the first meaningful line in the stack. That is the most important one. It skips a couple of unimportant things. This tool finds a lot of bugs that depend on the user's setup that we could never reproduce locally. I don't know, people having crazy digital rights management tools, or having crazy IT administrators, or you name it. The core of this functionality on Windows is this function, mini dump write dump, which, as the name implies, writes dumps. So that dumps your process state, and it's able to dump only the stack and all thread registers. So that creates a very small dump file, maybe 100 kilobyte on average. Microsoft provides symbol servers for all their system libraries. So we can take this mini dump on our backend and open it and symbolicate it and analyze it. That's super powerful, and nothing similar existed on macOS. There is Google Breakpad and Google Crashpad, of course, but that made a couple of very strange decisions. So we decided pretty early that we cannot use this, and we are always a bit averse of using a third-party code, but here especially. So Google Breakpad and Google Crashpad, they write Windows minidump files on all systems, even on POSIX systems. And that's not a very well-defined file format, well-documented file format. And then, of course, on POSIX, on macOS, nothing can open Windows minidumps. So then they had to write their own tools as well to open these minidumps again. So in the end, it turned out to be just a lot of code that now we would have to support when we include it in our code base for a not very powerful solution in the end. On the other hand, the Mac binary file format is very well documented. And that includes documentation for the core file format. The situation is a bit different on Linux, apparently, where the ELF binary file format is not that well documented, and you, at least not for the, it is well documented, excluding the file format for core files. And you have to check what GB does and replicate that. But all we had to do was check the macro core file documentation and write such a core dump that only included stack memory. And that was pretty simple, and we've open sourced that tool because it didn't exist, and I think it's pretty powerful. So whenever in any tool, Google Crashpad or in our tool, when you do error reporting, when you do error handling, and the process encounters an error or is about to crash, you want to delegate a lot of the error handling to an external process that is in a healthy state. And in order to do that on macOS, you have to send access rights to your process to the crash reporting process. And you do that by sending a message. You have to set up some communication ports, some kernel communication ports by name. And then you build a message. That message includes a reference to machtask self, which is the current process. And the message contains information to send access rights to that task to the other process. And then you send the message. And the other process waits for it and receives that task access right. And then the rest is a pretty straightforward going through the binary file format documentation, going through the list of macOS system calls and matching the two together. So you want information about all the thread registers. So you enumerate all the threads of your crashing process, and then you get all the register states for that thread. And you do that for all the threads, of course. And then you iterate over all memory regions of your crashing process. There's a helpful function, machvm region recurse, that enumerates all memory regions, and it will tell you which of those memory regions are actually containing stack memory. And then you create a mach binary file header describing that memory region. And when you've done that, then you dump it out into file. There's a binary file header, there's the thread information, there's the memory segment information, and then the copy of the actual memory contents, of course. You write that into a file, you can zip it for convenience, and then it turns out to be about the same size as a Windows mini dump, a bit larger maybe, but not much. And the result is a valid LLDB core file that you can just open in LLDB. It just contains less memory than a full core dump. You would need some additional metadata that Windows mini dumps contain that includes which shared library, which binaries were mapped into your process. We send that along in a simple XML file format. And then on the back end, you would need a couple of things. You need debug symbols for your own build. Everybody has that. You need to have the system binaries for all the macOS versions you support, because there are no symbol servers provided by Apple. That's actually relatively easy because there's such a small number of macOS releases. So we just set up 30 virtual machines and copied them all to a server. And then we have written and published a small wrapper around the LLDB API that will open these mini dumps we are creating, parse the metadata, look up the macOS binaries in our server cache, look up debug symbols for your own build, add them all into LLDB, and then LLDB symbolicates the stack trace for you. And you can even, that part is not published, but it's pretty straightforward how to do it. You can even analyze these bug reports automatically. So we've published this on GitHub. It's not in a form currently where it compiles as is. There are a couple of things that I've taken from our code base, but I've not shared, I've not made open source. It's like creating zip files, reading XML files, etc. Those would still have to be done. So here again, this point clearly goes to Windows. They had a great functionality that then we were looking for on macOS. So is there a question before I come to the last part? Or shall we just wait?
No questions on this section. This looks really cool. Please go on.
Okay. So like I said initially, ThinkCell also ships with a Google Chrome extension that lets you import data from tableau.com. And it's not only an extension, there's also a small web app involved that we host internally in our software that runs on localhost then, that lets you manipulate the data and map the data from Tableau to our charts, etc. So that was our first foray, let's say, into web app development. And initially we had to ask ourselves, so what language do we want to use? JavaScript was a hard no. I mean, nobody wants to do that really. And TypeScript was looking much better. At least it was reasonably type safe. And what was a great feature is that TypeScript has this large library of type definition libraries. So if you have to interface with a JavaScript library, Tableau JavaScript library, for example, then there's probably a TypeScript interface definition for that JavaScript library that makes that library type safe when used from TypeScript. And that was extremely useful. That was fun to write. The first version of our web app shipped in TypeScript. But now sharing code with C++ became impossible. And even in a small tool, pretty quickly we encountered, let's say, algorithms we had written in C++ already, we wanted in TypeScript, or just data structures, simple enums, whatever, that we had to copy between the two. So that was annoying. So we were looking into Emscripten a little bit and said, okay, maybe we can write web apps in Emscripten and just use C++ and compile it to WebAssembly. But that would have meant that all the JavaScript access loses type safety again. So it would look a bit like this made-up example here for an XML HTTP request, where I assume Emscript has a better API for. But this is what interfacing with JavaScript library looks like. It's a lot of strings, a lot of untyped checked calls, looking up global objects by name, looking up functions by name, and then calling them without checking for their arguments. So this is horrible. And then we thought, well, maybe we can combine the best of the TypeScript world and the best of the Emscript world and kind of mash that together and do what every developer, I think, dreams of, and that's build our own little compiler. And that compiler takes the type definition libraries from TypeScript. Here, an example for an HTML element, so for the HTML element JavaScript library. You see how it describes the properties in JavaScript and what type they actually have. We can take that, and we can take the TypeScript compiler, which is written in TypeScript and has a very powerful API. So here I have a very simple function in TypeScript, which takes a file name. It creates a program, which parses that file. Then I can get a reference to the source file I've passed in and iterate over all top-level syntax nodes in that file, and then ask the TypeScript compiler, is that a function declaration node? Is that a variable statement? And then I can dig deeper and ask, what are the arguments to this function? What are its return values, etc. So it's a very, very easy to use and very, very powerful API. And we put these two things together and build TCJS, which is our own TypeScript interface declaration compiler. It takes TypeScript interface definition files and compiles them to C++ interfaces that you can use from Emscript. So now you can make type-safe calls to JavaScript libraries by using Emscript. And actually, I think this could go even further, because Emscript internally has to rebuild type-safe, or currently rebuilds type-safe interfaces to all kinds of JavaScript libraries that are built in, to the DOM library, the OpenGL library, etc. And it builds kind of, I don't want to say C++, it builds C interfaces for those JavaScript libraries. And our tool could actually eliminate that work, and you can just auto-generate them from, as long as you have a TypeScript interface definition. So that's pretty powerful. It's almost self-hosting at the moment. That means it can almost compile the interface definition for the TypeScript compiler itself. It's still missing some TypeScript language features, but it's already very usable. And it was originally the master thesis of Yegor Suvorov, who I think is also participating in this conference. And he did this at ThinkCell, and that was really great work that I'm continuing now. And you should check it out. We are absolutely open for suggestion and for collaborators. And I won't go into too much detail here, because I hope to do a longer talk about this next year. But this is what the result looks. So this is the same TypeScript function that iterates over a TypeScript program, but in C++. So we have a transform function, and that now takes a JavaScript string as an argument. And we create a JavaScript array and call the JavaScript push function, all from C++, which will be compiled by Emscript to WebAssembly. And we call the TypeScript create program API, and then the for each child function, and pass it a C++ lambda, which we have to wrap so that the C++ lambda can be called from JavaScript. And then can iterate over the source file again and check, do we have a function declaration here, and translate that function declaration from a TypeScript interface definition to a C++ definition. So this is essentially how our compiler works. There's a lot of interesting work to do. There's also performance that we still have to optimize. And with that, I actually come to the end of my talk. So what are the conclusions that we have made after this work we have done? So the first one, I think it's almost the most important one, is that try to avoid what I call now premature unification in your code. Don't try to introduce cross-platform interfaces where you don't really need them, or where they don't fit the operating system that well. think about where you really need them and where your application needs a cross-platform interface. Then sometimes you have to unify object lifetimes across operating systems to make your life easier. You want to maintain invariance, strong invariance across operating systems. And state machines are a very helpful tool to do that. And you want to make your build tools and your backends cross-platform as well. And last but not least, of course, you want to always use C++, even if you're writing web apps, because that's just can be surprisingly fun. And well, with that, I thank you for your attention, and I hope you liked it. And now I'm open to all questions.
Okay, cool. Thanks a lot for the talk. A lot of questions. I will start from the. Denise writes, I had rumors about ThinkCell patching 4 binaries with custom machine code and extra hooks.
Sorry, can you repeat that? I hear your sound is a bit choppy. Can you repeat that?
The question about binaries for PowerPoint to insert extra hooks. So do you actually do this, and can you talk about it?
Yes, and no. It's also about a bit beyond the scope of the talk. But yes, on Windows especially, I mean, hooking functions on Windows is a very very common thing. Like every virus scanner hooks all kinds of system functions. And yes, we do that too. But other than that, it's a pretty complicated subject.
Okay, thanks. Probably we can touch on it in the discussion zone. Next question regarding shared memory. So what type of data do you store in shared memory?
That's a good question. It depends on which processes communicate. But let me try to go back to that slide. One of the original selling points when we were starting ThinkCell, and this is now, I don't know, 15 years ago or something, was that back then PowerPoint charts could not interface to Excel data. So if you inserted a PowerPoint chart, there was actually another process. It was Microsoft Graph, which has been now phased out. So you had a data sheet in which you couldn't enter formulas, etc. It was not very powerful, and the charts looked slightly, the charts. I think that was the problem. The problem was the data sheet was not very powerful, and the first selling point was that we were an add-in to Excel and to PowerPoint, and you could link Excel data to PowerPoint. So you could insert a ThinkCell chart, and we would open an Excel window, and you could enter your data, use formulas, whatever you were used to from Excel, and we would send that Excel data to PowerPoint and then create a chart out of that. So that was one of the most important original features, and that's also still a big part of the data we share here is, for example, data between Excel and PowerPoint, the Excel data. We send that over shared heaps. And it's the same with the Tableau API. We send the Tableau data via the shared heap. I think still in the JSON format, we get it from Tableau and then just send that to PowerPoint and parse it in our PowerPoint add-in. Really anything. And it's really our main inter-process communication mechanism.
Okay, great. Let's go to the next question. This from the lifetime logs. What do you think about using local AF_Unix socket abstract, not mapped to file bind address as process lifetime log?
Sorry, you have to repeat that too. There was also, I only got half of that.
Okay, the question is about using AF_Unix socket abstraction, which is not mapped file system, bind the address of process lifetime log.
Unix, what is it? Unix socket? Unix, you mean Unix sockets?
I actually, I personally am not aware of this thing, so I read it as I see in the chat, which is AF_Unix.
I don't know that either. I'll check it. Maybe we can see that afterwards in the discussion zone.
Okay, yeah, cool. And you can also just see the chat and answer in chat directly, I suppose.
Oh yeah, I see that. Okay, that's cool. Yes.
Okay, great. So the next question regarding these context per functions for translation. How much compile time do you save, and how much performance gain do you have from this approach?
I did not measure the compile time. I mean, in general, in general, we are pretty tolerant about our compile time. We buy pretty big computers to compile that. We make heavy. I mean, we have written and also published on our GitHub account our range library, and so our code is so heavy on templates in some cases that compile time is typically not our primary concern. And here, I mean, probably runtime. I mean, of course, runtime is better. There's zero runtime cost. But what would concern me most, especially in this cross-platform context, is, for example, if the translation call has to go to the disk and open the translation catalog. Is it in your macOS bundle or on macOS on the disk or somewhere? This is something that in a cross-platform context also always makes me headaches. It's just a case of problems, but when you're reading from the hard drive that you don't have if you just compile it, and that alone I think makes it worth it to me. I mean, did people start messing? People do everything. People start messing with file permissions. People delete files accidentally, and then this pops up in our bug reporter, and I don't want to see that. So every problem I avoid is good. That's almost more important than the probably real performance impact here.
Okay, and again, have nice compile time errors instead of runtime errors, right?
Do we get nice compile time errors in that context? If I think we do if you don't have the translation, yeah. Yeah, but that's built. It's something this doesn't create compile time errors because I think the tool that extracts the translatable strings runs during every build. So you just write your string and the build tool creates the translation output. But initially it will fill this thing here just with the English version until we get it back from the translators. So in that case here, it just always works.
Oh, all right.
It cannot fail, but you might not have a translation yet.
Okay, I see. All right, the next question is about the last part. And there seems to be a confusion about encryption and WebAssembly, which is not particularly clear. Whether you use encryption to compile JS to WebAssembly.
No, we compile. No, Emscripten does compile to WebAssembly. And Emscripten compiles to WebAssembly, but it also ships with the necessary. It also builds. That's why maybe that's where the confusion comes from. So the C++ code is transformed to WebAssembly. I mean, you can't transform C++ to JavaScript. But Emscripten produces a JavaScript file And that JavaScript file contains the, let's say, the linking of things. So there's a JavaScript file that is included in your HTML file. And that JavaScript file will then load the WebAssembly file and set up the interface, for example, between JavaScript and Emscripten. And sorry, WebAssembly. So that means, for example, in WebAssembly, I can, one way to, or that's how, let me start another way. That's how Emscripten lets you call JavaScript functions from C++, is that you can declare in C++ a function as a extern C function. And so it's a function that you have to import. And then you implement that function in JavaScript. This is actually how Emscripten internally works. And when Emscripten, the JavaScript wrapper around your WebAssembly, instantiates your WebAssembly object, it will also pass it the list of JavaScript functions that it knows. And then there's a linking step actually involved, where the extern C functions that you've declared in C++ are linked to the JavaScript implementation. And I think there were even blog posts on the Mozilla web team how they optimize these calls from WebAssembly over to JavaScript and vice versa. So these are super, super fast. So this is it's complicated. I always have to think again, what am I doing here? How does this really work? But I think that's how it really works.
All right, thanks. Yeah, I think this answered the question. We also have, it seems like this question about the file log, which is when we have two processes and we have degraded the log, etc., has not been answered. And personally, I do not get it completely too. So could you please go back to this slide? And the situation is we in the first process, we degrade the log, and then the second process acquires the exclusive log. So what happens with this locking call on the first process? So will it wait? Will it stop, or will it somehow acquire the log itself?
You mean what happens in this flog call in the first process when the second one comes along? Okay. Yes, this is a two-step process. This flog call releases a log, and then it waits until it can acquire a shared log. Yes. Because I call it here. I think it's a parameter to flog if you want it to wait, or if you want it not to wait. And here we want it to wait exactly for that case. So this one releases a log, then the second process succeeds with the open call, and we'll truncate the file again, and then both arrive here at the flog call, and then both of them will acquire a shared log. Yeah, the first process waits here, yes.
Right, but how the first process will be able to acquire a log when the second process will acquire exclusive log?
It will not. It will only acquire the shared log when the second process also arrives here. And then they can both get a shared log. So it will wait until the second process releases the exclusive log.
All right. Okay, cool. So do we have some more time for the questions, Tim?
I think only short one, because we have 1 minute 10 seconds left. So I'm not sure that there are short answers to any questions left. So I want to ask everybody to move on to the Zoom room and continue your discussion there. A lot of interesting questions was raised, and the topic on the WebAssembly and how you can port your C++ code there is pretty hard nowadays. Many people think about that, and yeah, Emscripten is pretty long there. So, but the next standard WASM, as I heard, is really promising, And I'm really looking forward to discuss that with you if you touch that already. We're gonna have a 30 minutes break further, so stay with us and have a good day.